let me know whenever you're ready. All right, so the median, then you compute it by taking 0.5 times 5, which is your formula. Yeah, that's the smallest observation, the next smallest one, and then that's the third one, right? 300,000. And then the mode is the one that appears on the data set the most often, 100,000. Okay, so I'll give you too much time for this one, 2 minutes. Okay. So what happened here then to get different answers? Why do we have answers on number 2 and 3? Because we didn't rearrange the data, basically, right? That's what I'm guessing, right? So when you compute in the median, the first thing you always want to do is rearrange the data, right? Otherwise, you're going to get the wrong answer. So this was a little trickier than I remembered. All right, so you would have to, like Christian was saying, you would have to rearrange the data to look like this. 2, 3, 3, 5, and 12, right? And then you know the median right away is this one, right? That's the median. And the mode is what? Happens to be the same thing. So the median and the mode in here are the same. So hold on, we have 9 people. Yeah, so there was 3 people that got that did not rearrange the data. All right. Well, that's wrong as well. So the answer should be 4, right? Okay, so this is the last slide in this section. I have 2 typos already. Let me write this down. Hold on. Okay, so you guys remember this discussion we had last week when we were building histograms, right? So in this case, now we're extending our analysis of what a distribution shape looks like. Okay, in this case, we have 3 different shapes. The shape all the way to the left is what we call symmetric, right? And we've talked about this last week. Okay, symmetric. The 2 shapes are called asymmetric or skewed. Right? Skewed. Asymmetric. Now, this one here is known as left skewed or skewed to the left. The reason for that is because it has a long left tail. Right? This is what's called a tail. That goes. Basically, you'll see more extreme values on the left side. Okay? So whenever the distribution shape has a long left tail relative to the right side, right? Then it's known as left skewed. Whenever the distribution shape has a long right tail relative to the left side, then it's known as right skewed or skewed to the right. But as far as the median and the mode are concerned, remember how we said that the median is less sensitive to outliers, right? Now, if we're going to find any outliers, we're going to find them in these 2 distributions, right? In the skewed ones. Not here, because everything is sort of close to the middle, right? But in this case, we know that if we're going to find any outliers, they're going to be where? On the left side, far away from the center. And in this case, on the right side, far away from the center. Okay? When we have outliers, what happens to the mean? The mean is actually impacted, right? It's affected. What happens to the median? It doesn't really move. All right? So this is why we have a case, whenever you have a left skewed distribution, the mean is affected by the very low values. So the mean is going to be lower than the median. Right? Because of extreme values on the left side, on the lower side of the distribution. Okay? Whenever you have a right skewed distribution, then the mean is going to be impacted as well but now it's going to be pulled to the right. It's going to be greater than it should be, let's say, right? So the median is going to be smaller than the mean. So in a way, a test of skewness, and this is just an informal test of skewness, right? If you see a data set and you compute the mean and the median are the same value, then you may be able to assume that the distribution is symmetric. Okay? But if you see that the mean is lower than the median, then you could infer from that the distribution is skewed to the left. And finally, if you see that the mean is higher than the median, then you could infer from that the distribution is skewed to the right. Okay? But the actual way of computing, of determining whether the distribution is skewed or not is by computing the skewness measure. There's an actual formula for that, which you won't see in your book. We won't see it here. Okay? All right. Okay. That's a summary, so let's move on. This is something I do want to quickly go over, because the summary of the differences and advantages. So what is the advantage of the mean? It's simple to use, to understand and use. We're familiar with it, and it uses all data, the whole data set to compute the measure. The problem with it is that it is affected by extreme values. The median, it is not really impacted by extreme values. The problem with the median is that it ignores extreme values, right? It basically, it does not use every single data value. Okay, it's just one of the values in the data set. Okay, and it ignores extremes. And it also takes much more time to compute, because you have to rearrange data, compute the index point. The mode is very useful when you have qualitative data, or when you have discrete quantitative data. But it's not useful for continuous data. All right, other measures that I won't go through here are the mid-range or the midpoint, the trimmed mean. I won't talk about them, but there are other ways besides the 3 that we've seen here, or the 4 if you include the weighted mean, that you can compute the center. Now, one of them, which is really useful if you are in business, I think, is the geometric mean, because it allows you to compute average growth rates. So when your data set consists of growth rates, let's say that you have a company, right, and you're looking at the last 20 years of sales revenue for the company. So you want to see what the change in sales revenue is over the last 20 years, right? So you can compute the percentage change, right? Year to year percentage change in sales revenue. You're going to have 20 growth rates or 19 growth rates. Now you have these growth rates, and you want to know what is the average growth rate. The best way of doing that is by computing the geometric mean. Okay, now again, I said I wasn't going to cover it here, right? So I won't. But I want you to be aware that there is this geometric mean that it's very useful for computing averages whenever you're dealing with growth rates, whenever your data consists of growth rates. So it's in business, of course, we use growth rates a lot, right? We want to see how earnings are growing, how sales are growing, and so on. Okay, how the stock price is growing, right? So now we get to the fun part. This is when we're going to see things that you probably haven't seen before, especially when we get to, not the range, we saw that last week, right? But these two here, okay? This is one of the, besides the z-score, this is one of the main discussions today. Let me check the time. We're good. All right, so now instead of measuring the center of the distribution, so what is a typical value in the data set, we're going to measure how spread out the values are in the data set. Are these values all near each other and near the center, or are they very spread out, right? There are 3 ways of doing it that we are covering here in class. The range, which has got many limitations, the variance, and the standard deviation. Now, the one that takes the most time to compute, and for a reason, is the variance. Okay? Because once you obtain the variance, going from there to the standard deviation is just one more step. But the one that really takes time to get to is the variance. Getting to the standard deviation is just one step away from what you got as the variance. Now these two numbers, or measures, the variance and the standard deviation, are very closely related. They are almost the same thing. They're one computation away from each other. Okay? But to get to the variance, it does take time. So one thing I want to remind you is that if you're dealing with sample data, you're going to have different notation than if you're dealing with population data. We saw that when we looked at the mean, right? But in the case of the variance and the standard deviation, not only will the notation change, but the actual formula will be different. Small difference. Okay? So be careful, right? If you're asked for the sample variance, the formula has different notation and it's actually different too. If you're asked for the population variance, you're going to get a different answer. All right. So the range. The range is something that we talked about last time. You take the highest value in the data set minus the smallest value in the data set, and there you go. The wider the range, what does that tell you about the data set? The values are more spread out. Of course, right? But that could be misleading. Because the range uses only how many values? Let me go here and ask the question again. Look at this data set. The data set is already arranged in ascending order, right? Starts with the lowest value and it goes all the way up to the highest value. All right? What is the range in this case? We'll take the highest value, 13, minus the smallest value, 1, 12 is the range. Okay? Now what if I do this? What if I change this 13, just this one number, and I put a 130 there? So I put a 0 here. What would happen to my range? It would be a lot higher. It would be what, 129? It would go from a range of 12 to a range of 129. Now, is that an accurate measure of dispersion, 139 in this data set? Not really, right? I mean, if you raise this thing and you put a 130 here, your range is 129, but most of your values are near 8 or 9, right? I mean, the data set is not that spread out. The data set is all the data points are very close to each other, really, right? But just because you have one extreme value, your range blows up. So you gotta be really careful about using the range. You do wanna using the range is simple, it's easy to do, right? But you wanna use it whenever you don't have extreme values, whenever you don't have outliers. Because if you have outliers, that's gonna really give you a misleading measure of dispersion or variation, okay? So one of the main limitations of the range is that it only uses 2 data points, right? It ignores everything else in the middle, right? It uses the highest and the lowest, and that's it. Which makes it sensitive to what? To outliers, because where are the outliers? On the high end or the low end, that's where the outliers would be, right? Not in the middle, okay? So it uses only 2 data values, which makes it sensitive to outliers. Therefore, if you have outliers in your data set, you could have really misleading information coming out of the range. So do we use it? Sometimes. But not as much as this one. I talked about all this. Not as much as this one, all right? So this, I would say this is our first big formula of the course. This is when things start getting a little challenging. That's what I get from the feedback that I get from teaching this course. Maybe for this course it would be a very straightforward discussion. So do you see why I put emphasis on the notation before, right? Because now we're looking at the same type of notation. Okay? Notice one thing. This formula here, it's the sample variance. Not the population variance, the sample variance. I'll give you a second to write it down because I see that you are doing that. You could also print out the slides, right? It may be easier. Now, the label that we use for the sample variance is S squared. That's the label, right? Just how the sample mean is known as X bar, right? The label that we use for the sample variance is S squared. So I'm going to do it in two different ways. I'm going to compute a sample variance using the actual formula structure, and I'm going to also do it in a table format, like an Excel type computation, because it's much easier that way. Right? Now look at this. Look at the formula. The formula is saying what? The sample variance, which is labeled as S squared, is equal to what? Two numbers. You need two numbers, right? You need the numerator and denominator. Okay. Now down here, pretty simple, right? N minus 1. What is n? Sample size. Up here, you're like, that's a little messy. What exactly do we have up here? We have xi, which is basically the data values, right? x1, x2, x3. But we also have what? X bar. What is x bar? The average of the data set. So notice one thing. Before you can even compute the sample variance, you have to compute what? The mean. Otherwise, you won't be able to compute the sample variance. So before you can compute the sample variance, you must compute the sample mean, x bar. Because you're going to use that in your computation of a sample variance. So let's go through the computation first, and then I'm going to interpret what it is actually telling you. Really easy data set. 3 observations, yes, so we don't waste time, because if we have 3 or 200, it's going to be the same. Okay? I'm going to put it here. xi. I'm going to make up these numbers, right? 6, 10, and 4. No, that's bad. And 5. Yeah, it's better. Is it better? Yeah, it's better. All right. So we have, what is the sample size of this data set? N equals 3. What is the average? X bar is going to be 6 plus 10 plus 5 divided by 3, 7. We have the sample size, we have the average. Now we need to do what? We need to use that information because, notice, sample size and average, they're needed. Both are needed, right? And what else is needed? The actual data, of course. Okay? To compute the sample variance. Now, if you guys can do it for this data set, you can do it for any data set. Any data set, right? If I give you 10 observations, it just takes more time. Okay? So let's do it for this data set. What is this sample variance equal to? S squared. Well, the way to read the formula is this. Well, there are two pieces of information, right? There's the top number and the bottom number. Okay? Down here, what do we have? 3 minus 1, just 2, right? I'm going to write it out. 3 minus 1, okay? But up here is where it's going to take a little more work. So up here, we're saying this. You got to take each observation one at a time. So start with the first observation, x1, right? Minus the average. That's going to give you what's called a deviation, also known as x in deviation form. How far is x from the average, right? X minus the average. Take that difference, that deviation, and square that. And then do what? Do it for the next one, and for the next one, and for the next one, right? And you're going to get a bunch of terms. Add them up. That's what this means. Add them all up. All right? So this is what it's going to look like. What is the first observation that we have? 6, right? So that's x1. Take 6 minus the mean, which is 7, and take the difference, which in this case happens to be -1, right? Square that. Now do what? To that number, to whatever you got to add the next observation's deviation squared. What is it? 10 minus 7 squared plus the last one, which is 5 minus 7 squared. So I'm going to write it all out, right? I guess I'll do it once. Here you're going to have 2, right? Down here. And up here you're going to have what? Let's go through it together to make sure we can get this down, right? Brittany, what do we have out of this first term? Which is 1. Good. So 1, and then what? Plus what?
4a squared, so 9.
Plus?
-2 squared, so 4.
Yes. So that's going to be 14 divided by 2, right? 7. That's the answer. Let me say it again. If you can do it for this set of numbers, you can do it for any set of numbers. the difficulty does not increase with the amount of work, right? It's just doing more of this, right? More observations. Okay. You may have questions. I know you may ask, why do we do n-1? I would love to talk about it, but we won't. Okay. Just notice one thing. This is a sample variance, right? And the formula has sample notation. Notice the x bar is a sample mean. Notice the n, small n, is a sample size, right? And don't forget that in the case of a sample variance, we actually take the sample size minus 1. Don't forget that, okay? All right, now I said I wanted to do in a table format. So let's do that. So if you're doing this in Excel, you want to do this. You want to have rows and columns, right, in Excel. So you want to come up with a column next to your data that has the values of x bar, which is the same value, right? It's fixed at 7. 7, 7. Then you want to take xi minus x bar in a third column here. And you have -1, 3, -2, right? Then you want to create a new one in which you squared these deviations, 1, 9, 4, right? This is known as x in deviation form because you're taking x minus its average. How far is x from its average? And this is the squared deviation, right? The deviation squared. What's the next step? Add them up. So these three numbers, we add them up. So we can do this, right? So we have a column total of 14. Is that the variance? No. The variance will be 14 divided by 2. So s squared is equal to 14 divided by 2, which comes from 3 minus 1, right? 7. So I prefer to do it this way because it's more organized. Okay? And that's how you would do it in Excel. All right, now let's look at what happens if we are looking at the population variance. What do you think should happen? So can you tell me what would you change here? If we're looking at the population variance, Alex, yeah.
You would change the sign. Like instead of s squared, it's going to be
Something else? It has to be, right? Because if you don't change the label, then you don't know which one you're talking about. Sample or population variance, right? So one thing is going to change for sure is this thing. Like in the case of a mean, it was x bar and mu. What else is going to change? Who's there? N minus 1. Instead of small n, what are we going to use? Large n. There's something else that's going to change here besides just the, yeah. And what else would change? X bar. Instead of x bar, what do we use? Mu. Right? Some things are just changing the notation, right? But there's something here that will actually change your computation. So let's, I just did this, right? So I won't do it again. Let's look at the population variance, and I'll come back to standard deviations. Like Alex said, what changed here? Instead of S, we use sigma. Remember we use Greek letters for population labels, right? So small sigma, lowercase sigma, right? Sigma squared. That's the population variance. Up here, instead of x bar, what do we have? Mu, population mean. Here, instead of small n, we have uppercase N, population size, right? So it's making changes in notation. But the one thing that is really different when you go from the sample variance to the population variance is that you don't take the population size minus 1, okay? You just divide by the population size. Is that all right? So that little minus 1 adjustment only happens in the sample variance formula. It does not happen in the population variance formula. Okay? So to me, that's the biggest difference.
Is that because the sample is within the population, that's why you're subtracting by 1 from the sample?
Yeah, so the reason why you subtract 1 from n is because the sample variance is going to be an estimate of the population variance. And to make the sample variance an unbiased estimate, you need to subtract the 1. If you don't subtract the 1 from the sample variance formula, then your estimate will be biased. Okay? But we haven't defined what biased or unbiased is, so we should stop there, right? Okay? you sort of have I can say it because you have some idea of what bias and unbias is, but statistically we have a specific definition that we probably won't get to until after the midterm. All right. Now, let's talk about the sample. So we go back to sample notation, right? This is the sample standard deviation. What's changed? Remember how I said that when we go from variance to standard deviation, there's only one additional computation to make, right? What would that be? Square root. What's the difference between the variance and the standard deviation? That the standard deviation is the square root of the variance. That's it. So if you can get to the variance, then you're one computation away from the standard deviation. Just take the square root of it. All right? So what is the label for the sample standard deviation? S. Of course, right? It works out perfectly. Square root of S squared, S. So now we can talk about why do we have two measures that are so similar, right? The variance and the standard deviation. They're almost the same. They're just one computation away, and they measure the same thing. They measure what? How much variation there is across data values in a data set, right? Is there a lot of variation or not? Is there a lot of dispersion or not? Okay. Are the data values close to each other, or are they really spread out, right? Well, the higher the variance, the more spread out the values are, or the more variation there is. The lower the variance, the less variation. Same with the standard deviation, right? Because they both measure the same thing. Okay? So why do we have two then? Because the main reason why we have two is because the variance is difficult to interpret. It's hard to interpret the number that you get from the variance. Let's look at this. Let's look at this example that I used before. Now, let's say that these are, we need to create a context, right, to interpret. Let's say that this is hourly wage in dollars, right? Of course, it's illegal to have this hourly wage, but that's fine. That's the example I used, okay? Let's say that this is hourly wage in dollars, right? 6. So one person makes 6, the other one makes 10, the other one makes 5 per hour. All right? Your original data comes in the form in what units? Dollars, right? That's it. But when you go through the computation of the variance, what are you doing? You're taking the mean, which is $7. That's right? That's the average wage in this data set. You're looking at the difference between the mean and the actual observations, and then you're squaring that difference. So when you square that difference, what are the units of these values? Anybody? What are the units of these values? Dollars, right? $6, $10, $5. What are the units of these values? They're dollars squared. That's the units. The units changed. $2 squared. Now you're adding up these numbers. This is $14 squared. So this is $7 squared. How do you interpret that relative to your original data that is in dollars? So what does this really mean? I don't know. I don't really know what it means. One thing I know, that the bigger this number, the more variation there is. Meaning this, if I create a new data set, and I call it yi, and let's say we have 5, 28, and 12, right? You can tell that there is more dispersion in this data set, right? The numbers are further away from each other, yes? In this case, the numbers are closer to each other, right? So if you compute the variance of this, you're going to get a higher number than 7. Is that all right? So what I'm saying here is that if you have two data sets and you compute the variance of both data sets, you can compare the two to decide which one has higher variation, right? The data set with the higher variance has higher variation, right? But that's the only way to really use it. If you only have this and you only have one data set and just one number, 7, what does that mean by itself? Is that high, low? You don't know. Can you interpret this number? Not really, because it's $7 squared. How do you even interpret that? Okay? So to get rid of this interpretation problem, right, what we do is we take the square root of it. So we say S equals the square root of 7. What would that be?
2.65.
Thank you. 2.65. Now, what are the units of this number now? Dollars again. So now we can take this number and actually interpret it within the context of the data set, right? So what can we say? 2.65. How will you interpret that? Yeah.
That's how like far apart the hourly wages are from each other, like on average.
Yes. Right? Listen to the name. Standard deviation. It's like typical deviation, right? Like an average deviation, if you will. Okay? 2.65 can be interpreted as the typical deviation of a value in the data set from where? From the center. Look, take the value minus the center, right? How far is this value from the center? $1 away to the left, right? That's why it's -1. How far is this value from the center? $3 away to the right. How far is this value from the center? $2 away to the left. So if you look at these deviations, what is a typical deviation? 2.65, that's typical, right? Around 2. That seems reasonable. Well, the variance says what? 7. That's crazy. That's way too much, right? Why? Because this is dollars squared. Okay? So what you do to make it, to be able to interpret is you take a square root, and now you can say the typical deviation of one of the observations from the center of 7 is $2.65. Okay? So you're measuring variation, distance across observations from the center. Okay? The good news is that you can measure that using the same data as the original data set. Sorry, the same units of measurement as the original data set. All right. So very useful, standard deviation. It's going to be very useful for us. We're going to see it again later today. We're going to see it over and over and over again. How many of you have seen this for the first time? Standard deviation. Okay. So I guess you've heard about it before, the rest of you. Very important that you understand how to interpret it. Okay? Especially how to interpret it. Because later on, we won't have to compute it. Beyond chapter 3, we won't have to compute it. We're going to be given the number in different applications, basically, and we're going to have to use it and interpret it. Okay? So that's the most important part. So if you can get the variance, then you can get the standard deviation. All right? All right. I'm not going to go through this example because we just went through one here. But I do want to talk about this. The population standard deviation. Look at the formula, how it's changed. Well, it's the same thing, right? Take the variance, which is what's inside, and do what? Square root of the variance. Okay? So how do you get the population standard deviation? Compute the population variance and take the square root. It's nothing different. Okay? Why is the variance and the standard deviation, why are they better measures of dispersion than the range? Because the range, like I said, does not use all information in the data set. It only uses the highest and the lowest value. It ignores everything in the middle, right? Because the range is very sensitive to outliers. Now, I'm not saying that the standard deviation and the variance are not sensitive to outliers. They are sensitive to outliers, right? Because they incorporate those outliers in the computation, but not as sensitive, right? The range uses basically the extreme values to compute the measure of dispersion. The variance and the standard deviation use all the values to compute the standard deviation. What's the problem with the variance and the standard deviation? Well, besides the interpretation issue that we talked about for the variance, the other issue is that it's time consuming computationally, right? It takes time to go through the whole computation. Okay, but once you work for a company, you learn how to use Excel, and it just does it for you. All right, it's really easy. You don't do any work. Just highlight the cells, click here, click there, and that's it. So why don't we answer this question, and then we can take a quick break after we answer this one. So I'm giving you 2.5 minutes on this one because it takes a little more time. I know that only 5 people responded probably because of time constraints, right? But I know on the exam you may take more than 2.5 minutes for this one, like maybe 3, 4. That's fine because you'll save time on other questions, right? But on average, this is what you should be using up as far as time is concerned. So we all got it, right? Let's see if my answer is right. Good. So we agree on this one. Okay. Let's take a 15. We talked about the standard deviation, right? There's one last technique that is used to measure dispersion or variation. Okay, we're in that section, right? Central measures of dispersion, right? Like the range, variance, and standard deviation. There's one more called the coefficient of variation. This is not as popular as the standard deviation, but I've seen it used. You know, my field is finance. I haven't seen it used very often, but I've seen it used before. Okay, in research papers and stuff like that. But it will be in most standard statistical books. All right. So the coefficient of variation is basically going to measure the standard deviation as a percentage of the mean. So as far as the formula is concerned, it's really, really simple, right? So it's more about understanding what it measures. How is it different from the standard deviation, right? The coefficient of variation is going to take the standard deviation and it's going to divide it by the mean. That's it. That's all it is. If you want to make a percentage, multiply times 100, right? If you want to express it in percentage terms. Now, why would you do that? Because you may have two different data sets that have different means. I think it's better if we think about it this way. You may have two data sets in which the units of measurement are different. Okay? So remember how the standard deviation tells you about variation within the data set in the units of measurement as the original data, right? Same as the original data, okay? But what if you have this? What if you have housing prices, okay? Housing prices in the US and housing prices in Japan, okay? In the US, housing prices are in the data set. When you look at the data set, right, you have US house prices. The data set comes in the form of dollars, right? And then you have in Japan, you have also a set of housing prices, right? The data set comes in the form of yen. Now, you have two different currencies, right? What you're interested in is how much variation is there across different house prices, right? How much variation? And you want to compare across countries, right? The problem is that your data is coming in different currencies, in different units of measurement. This is dollars and this is yen. Well, what's the difference between dollars and yen? There is a conversion ratio, right, of 1 to 100, let's say. I don't know what it is. 1 to 80, 1 to 90, who knows, right? $1, 100 yen. That's probably completely wrong. But it's close enough, okay? $1 equals 100 yen. So the numbers here are going to be much smaller than the numbers here, right? So when you compute the standard deviation here, and you compare for the US, and you compare it to the standard deviation for Japan, most likely this number is going to be greater, right? Simply because the units of measurement are just bigger numbers, not because there is more variation. Does that make sense? So basically, the standard deviation and the variance is affected by the units of measurement of the original data set. So it's hard to compare data sets when you have different units of measurement. So to overcome that issue, what we do is we compute the coefficient of variation. Right? We express the standard deviation as a proportion or percentage of the mean. So we get rid of the units of measurement completely. And now the two numbers will be comparable. So do you want to compare these two? Probably not. Do you want to compare the coefficient of variation in the US to the coefficient of variation in Japan? That's probably what you should be doing. Because in this case, you don't have an issue with the units of measurement. Okay? So how do we compute it then? Like this. Now, notice there are two formulas, right? Formula 1, Formula 2. What's the difference? We should know by now, I hope. Just the different data sets. In this case, we have a subset. In this case, we have the whole thing, right? Sigma divided by mu, S divided by X bar. Same exact thing as far as computation is concerned, right? Again, you multiply times 100 just to make it a percentage number, but you don't have to. You can leave it as decimals. Is that right? You don't have to multiply that, but you know the formula has 100 there, but that's just a cosmetic adjustment. Okay, it's really nothing that matters that much. So there's really one formula here. That's what I'm trying to say. There's one formula here. It's just different notation for different types of data, population or sample. All right, so let's look at an example here. So if you want to know what the formula is, it's the standard deviation divided by the average times 100. That's your coefficient of variation, right? If you want to keep it up here, okay? All right, so look at this example. We have a stock A. That's a stock from a company, right? The average price last year was 50. That's your average, your mean, right? 50. And the standard deviation was 4. What is the coefficient of variation? 4 divided by 50 times 100, 8%. So how big is the standard deviation? It's 8% of the size of the mean. Okay, that's what we're saying, right? The standard deviation is 8% of the size of the mean. We're expressing the standard deviation as a percentage of the mean. When you look at stock B, notice one thing. Stock B has, and this is probably a bad example. It would have been much better if this were a 4, but it doesn't matter, okay? Stock B has an average price of 100, a much bigger average price, right? Prices are higher. It's like, you know, you have penny stocks. Have you guys heard of penny stocks? There are stocks that trade at prices of under $5, right? I was talking to a friend. What friend was this? It's like 2 days ago. I don't even know anymore. Okay, some friend, all right? And oh, my brother-in-law. It wasn't a friend. Okay, so and he said that he invested money into this penny stock. It was like 23 cents per share, right? And now it's at 2 cents per share. So he was freaking out because he lost like $15,000 on this thing, right? They're very high risk stocks because it's basically like a new idea, a new venture. Somebody raises capital, they incorporate the thing, they put it on the stock market, right? But you don't even know if the thing is going to work, right? So it's really high risk, high returns too, if the company, if the project works out, right? So that's a penny stock, right? So penny stocks trade at what? Cents of a dollar, right? 23 cents, 24 cents, $1.20, and so on. There are other stocks like Apple that trade at what prices? $600, right? $700. So when you take the average prices of these two different stocks, you're going to get completely different averages, right? So when you take the standard deviations, they're going to be very different, right? Apple may be a much more stable stock in terms of the price not moving much. So the standard deviation is actually should be low, but because it's already trading at high prices, the number will be big, right? Compared to a penny stock that trades at cents of a dollar, right? That's the problem here, right? So you have this stock that trades at really high prices, the average is 100. You have this stock that trades at low prices, half the size, 50. They both have the same standard deviation, similar, right? Not the same, similar. But which one is more stable? Which one has less variation? Obviously this one, right? Okay, even though the standard deviation is slightly higher, really this is the most stable one, the more stable stock, right? Because the prices that this stock trades at are much higher. So how do you figure that out? What you do is you take the standard deviation and you divide it by the price, right? And you see that this is much higher than this. Even though the actual standard deviation is lower here, it is higher as a percentage of the average, okay? So if you look at standard deviation, what will you conclude? This stock has prices that are more variable, but that's misleading, right? It's not more variable. This stock actually has prices that are less variable than that one. You know, when you take into account the units of measurement, okay? That's the benefit of the coefficient of variation, all right? Good. So we get to our third bullet point, which is measures of association. There's one technique here that I had to go looking for in your book. I found it in chapter 14, and I took it and I moved it to chapter 3, because it should be in chapter 3. Impacted by extreme values. The problem with the median is that it ignores extreme values, right? It basically, it does not use every single data value. Okay, it's just one of the values in the data set. Okay, and it ignores extremes. And it also takes much more time to compute, because you have to rearrange data, compute the index point. The mode is very useful when you have qualitative data, or when you have discrete quantitative data. But it's not useful for continuous data. All right, other measures that I won't go through here are the mid-range or the midpoint, the trimmed mean. I won't talk about them, but there are other ways besides the 3 that we've seen here, or the 4 if you include the weighted mean, that you can compute the center. Now, one of them, which is really useful if you are in business, I think, is the geometric mean, because it allows you to compute average growth rates. So when your data set consists of growth rates, let's say that you have a company, right, and you're looking at the last 20 years of sales revenue for the company. So you want to see what the change in sales revenue is over the last 20 years, right? So you can compute the percentage change, right? Year to year percentage change in sales revenue. You're going to have 20 growth rates or 19 growth rates. Now you have these growth rates, and you want to know what is the average growth rate, right? That's the median. And the mode is what? Happens to be the same thing. So the median and the mode in here are the same. So hold on, we have 9 people. Yeah, so there was 3 people that that did not rearrange the data. All right. Well, that's wrong as well. So the answer should be 4, right? Okay, so this is the last slide in this section. I have 2 typos already. Let me write this down. Hold on. Okay, so you guys remember this discussion we had last week when we were building histograms, right? So in this case, now we're extending our analysis of what a distribution shape looks like. Okay, in this case, we have 3 different shapes. The shape all the way to the left is what we call symmetric, right? And we've talked about this last week. Okay, symmetric. The 2 shapes are called asymmetric or skewed. Right? Skewed. Asymmetric. Now, this one here is known as left skewed or skewed to the left. The reason for that is because it has a long left tail. Right? This is what's called a tail. That goes. Basically, you'll see more extreme values on the left side. Okay? So whenever the distribution shape has a long left tail relative to the right side, right? Then it's known as left skewed. Whenever the distribution shape has a long right tail relative to the left side, then it's known as right skewed or skewed to the right. But as far as the median and the mode are concerned, remember how we said that the median is less sensitive to outliers, right? Now, if we're going to find any outliers, we're going to find them in these 2 distributions, right? In the skewed ones. Not here, because everything is sort of close to the middle, right? But in this case, we know that if we're going to find any outliers, they're going to be where? On the left side, far away from the center. And in this case, on the right side, far away from the center. Okay? When we have outliers, what happens to the mean? The mean is actually impacted, right? It's affected. What happens to the median? It doesn't really move. All right? So this is why we have a case, whenever you have a left skewed distribution, the mean is affected by the very low values. So the mean is going to be lower than the median. right? Because of extreme values on the left side, on the lower side of the distribution. Okay? Whenever you have a right skewed distribution, then the mean is going to be impacted as well, but now it's going to be pulled to the right. It's going to be greater than it should be, let's say, right? So the median is going to be smaller than the mean. So in a way, a test of skewness, and this is just an informal test of skewness, right? If you see a data set and you compute the mean and the median are the same value, then you may be able to assume that the distribution is symmetric. Okay? But if you see that the mean is lower than the median, then you could infer from that the distribution is skewed to the left. And finally, if you see that the mean is higher than the median, then you could infer from that the distribution is skewed to the right. Okay? But the actual way of computing, of determining whether the distribution is skewed or not is by computing the skewness measure. There's an actual formula for that, which you won't see in your book. We won't see it here. Okay? All right. Okay. That's a summary, so let's move on. This is something I do want to quickly go over, because the summary of the differences and advantages. So what is the advantage of the mean? It's simple to use, to understand and use. We're familiar with it, and it uses all data, the whole data set to compute the measure. The problem with it is that it is affected by extreme values. The median, it is not really. Let me know whenever you're ready. All right, so the median, then you compute it by taking 0.5 times 5, which is your formula. Yeah, that's the smallest observation, the next smallest one, and then that's the third one, right? 300,000. And then the mode is the one that appears on the data set the most often, 100,000. Okay, so I'll give you too much time for this one, 2 minutes. Okay. So what happened here then to get different answers? Why do we have answers on number 2 and 3? Because we didn't rearrange the data, basically, right? That's what I'm guessing, right? So when you're computing the median, the first thing you always want to do is rearrange the data, right? Otherwise, you're going to get the wrong answer. So this was a little trickier than I remembered. All right, so you would have to, like Christian was saying, you would have to rearrange the data to look like this. 2, 3, 3, 5, and 12, right? And then you know the median right away is this one.